set this integral up as a triple integral, set the volume up as a triple integral using cylindrical coordinates, you get to say theta goes from 0 to 2 pi, r goes from 0 to root 5, and z goes from square root of 4 plus r squared to 3. Remember your Jacobian, r dz dr d theta. Okay? And then just like Andrew, right? What's your name? Andrew. Just like Andrew said, the question asks it to be a double integral. So we go 0 to 2 pi, 0 to root 5, and then we evaluate this thing. There's no z, so it's just the length of the interval, and the length of the interval times r filters through 3 minus square root r squared. Okay, so now this is a double integral. We just did the first integral, and now we got a double integral. So we're good here. Okay. So this is pretty easy. This was pretty easy. Okay. That's all we're going to say about it. So let's take a second look at it. I want to introduce a problem using this exact same setup, just a little different. I want to change this from z. Are we good here, or do you have any questions? Okay, cool. I want to change this from minimizing it with the xy plane. I want to move that up so our shape looks a little different. Okay. I want to move this z equal to 0. I want to move it up to 2.5. So what does that do? This goes away, first of all. And I grab this plane and I move it up, so now I got another plane crashing in right here. Okay, so if I blow up my shape, it looks like this. It's got a circle here and a circle here, and it's got hyperboloid ends. Coffee mug, okay? No handles. Alright? So what happens when I do this? Okay, well let's take a look. So typically you would be tempted to say that z goes from 2.5 to 3. Right? Because as z travels, you go from 2.5 to 3. And that makes sense. Okay, let's think of cylindrical coordinates. Z goes from 2.5 to 3. And well, for cylindrical coordinates, we would say that r goes from 0 to square root 5 still, and theta goes all the way around. Okay, but that's wrong. What is this actually describing? Who can tell me? Z goes from 2.5 to 3, r goes from 0 to square root 5, and theta is going from 0 to 2 pi. What is this describing? A perfect cylinder with with height 0.5 and radius root 5. Okay, that is not the shape. This shape has curved edges. Okay, so how do we deal with this? All right, we just look at it first glance. You would want to do this, but this is wrong. We can't do this. So here's what we do. Let's keep our old bound. So let's keep our old bound of 4 plus r squared. Okay, this completes the bowl, right? Well, let's let our radius take care of the fact that we don't have all of the bowl. Okay? So we need this curved bowl shape. So that's why z has to go from root 4 plus r squared to 3. Because we need the curved bowl shape. But now when we compress this onto the xy axis, what do we have? We don't have a disc anymore, we have a punctured disc. Okay, we have a disc with a smaller disc taking out. Alright? So what's changing here is, even though we changed the problem, z's still going from the hyperboloid to the plane, but the radius is no longer traveling from 0 to square root 5. We got to see where the radius travels from. The radius, when we project it on here, we have this punctured disc. Right? Does this make sense? Okay, yeah. So we're going to let the radius basically limit our entire shape. We typically like to limit the entire shape with whatever z doing, but in this case we can't, or else we'll just end up with a cylinder. So we let the radius limit what z is doing by figuring out what the radius is going to and from. It's not starting at 0, it's starting at whatever this is. Well, what is that? That is where square root of 4 plus r squared is equal to 2.5. That's going to draw out, how I'm going to solve for my radius right here. Okay? Just like the big one is when I set it equal to 3, the small one's going to be set where I set it equal to the other plane. We're just intersecting this plane and projecting it. We had this intersection projected it, now we got to have the second intersection and project it. Okay? So let's do that real quick, and we see that, well, I can't just call this one 5 in my head. I have to write it out. So this is, we'll change this to 5 halves so I can do my, whatever I have to do to it, whatever it's called, math. Okay, so 4 plus r squared is equal to 25 fourths. So r squared is equal to 25 fourths minus 16 fourths. Like the rest, that's 9 fourths. And r is going to equal, to 3 halves. Okay. So now we have z changing from giving us the bowl shape, and r telling us how much of that bowl we're taking. So r is going from 3 halves up to 3. And theta still gets to go all the way around.
Travis.
Yes.
Why isn't it going to root 5?
Yeah, it is going to root 5. I don't know why I said 3. Yeah, so you plug in 3 here and solve for when it was 3, and that gave you root 5. I'm sorry. But theta is going from 2 pi. I didn't need to erase that. Okay. So the projection onto the xy plane helped limit our shape. You know, if you just looked at this, you would think, okay, well, z is going from down here to up here. Really, that's not going to give you the right shape. That's going to give you a cylinder. You need d to travel from this bowl shape to the plane. Okay? And let r take care of getting rid of this bottom part. Are we all clear on that? Cool. All right, so with that, we'll move on to the second problem, unless there's any other questions. Okay?